We finished our last video showing this figure. It represents a mass of fluid that we've isolated from a larger mass, as we can see. There are two types of forces that can act over it. One of them is represented by the forces that act over the surface of the fluid mass. Let's call them surface forces. We can see that they can be tangential to the surface or normal to it. The other type is related to the quantity of matter. Let's call them mass forces. It's necessary that the mass is immersed in a force field, like the gravitational field. So we can call them field forces. In this case, the mass force will be the weight. We've seen something about the surface forces in our last video. When a tangential force was applied on the superior plate, the fluid between the plates was deformed, and the ratio between the force and the area was called tangential stress or shear stress. Now let's consider this case in which a normal force is applied to the superior plate. The ratio between the force and the area, here expressed in its differential form, is called normal stress or pressure. We'll start seeing in this video how the pressure varies in the atmosphere and inside the liquids. We'll begin by deriving a general expression that we'll call fundamental equation for static equilibrium. For this purpose, let's consider a generic mass of fluid referred to an XYZ coordinate system. The z-axis is in the vertical direction. The x and y axes are horizontal, generic, and perpendicular one to another. I is the unit vector along the x-axis. J is the unit vector along the y-axis. And k is the unit vector along the z-axis. Now let's consider a point P in which the pressure is P. It's at the center of an imaginary parallelepiped, whose faces are parallel to the planes XOZ, YOZ, and XOY. Its dimensions are the x, the y, and the z. Let's assume that the pressure variation along the x, y, and z coordinate axes are dp over dx, dp over dy, and dp over dz, respectively. The component of the resulting pressure forces along the x-axis will be given by this expression, which results in this one. If we do the same to the other axis, we'll find this expression for the y-axis and this expression for the z-axis. This will be the result vector, which comes to this. Well, we'll need some room for the algebra. The expression above is the vector expression which represents the result force caused by the pressure and its variations inside the fluid. But we can't forget the mass force which acts over the parallelepiped. Here it is. Now, the result force that acts over the parallelepiped includes the surface force and the mass force. If the parallelepiped is in equilibrium in the interior of the fluid, then R equals 0. Then we can write this, and this, and this, and finally this small expression that we were looking for. Ladies and gentlemen, here it is, the fundamental equation of static equilibrium. Let's take a look at this expression. At usual conditions, there is no pressure variation over a horizontal plane, say, along the x-axis and the y-axis. It varies along the z-axis. Pressure gets smaller when we go upward, and it varies with the density of the fluid and with the gravity. Now, all we gotta do is integrate. The integration of this expression depends on the knowledge of how ρ and g vary with z. In general, for engineering purposes, we can assume that g is a constant. Check its values in this table. Okay, g will be constant in our studies. Thus, let's see how ρ varies with z. We'll begin considering the case in which the fluid is incompressible, which means ρ is constant. The integration leads to this expression, and to this, and to this. See this graph. The axis y is not seen because it's perpendicular to the screen. So the x-axis represents a horizontal plane. If P0 is the pressure on it, the pressure at the elevation z will be P0 minus gamma z. Now, if we consider an h-axis also vertical but positively oriented downward, then we must write P equals P0 prime plus gamma h. I'm sure I've seen this before. I may be wrong, but something's telling me that Mr. Simon Stevin has something to do with this equation. It certainly has. There's a video on this channel talking about the Stevens law. I'll leave the link on the description. And so we go sailing on the sea of fluid mechanics. It's fun, isn't it? In our next video we will see what happens with compressible fluids. Oh, and if you like this video, don't forget to give it a like, comment, share and subscribe. Hit the bell so you can be notified of my next videos.